Okay, so today's video, we're going to go over sections 4.1 and 4.2 because of us needing to have time during the week for the exam one. So we're going to go over functions of several variables first. So our learning objectives: recognize a function of two variables and identify its domain and range. Sketch a graph of a function of two variables. Sketch several traces of level curves of a function of two variables, and recognize a function of three or more variables and identify its level surfaces. So here's our definition. A function of two variables, z equals f of xy, maps each ordered pair xy in a subset D of the real plane R squared to a unique real number z. The set D is called the domain of the function, and the range of f is the set of all real numbers z that has at least one ordered pair xy in which it's an element of D, such that f of xy equals z as shown in the following figure. So, all right. Let's go over our first example. I think I split this up into two, so we have plenty of room. Except that you guys all know that I write big. Second. Okay, sorry about that. All right. So, assuming the recording is live again, so let's look at the first example. Find the domain and range of the following functions. So we're going to go with part A here. So we have f of xy equals 3x plus 5y plus 2. So this is an example of a linear function in two variables. There are no values or combinations of x and y that can cause f of xy to be undefined. So the domain of f is r squared. To determine the range, we first pick a value for z. We need to find a solution of the equation. Find f of xy equal to z. Or in other words, 3x plus 5y plus 2 equal to z. One such solution can be obtained by setting y equal to 0, which yields the equation. So if we let y equal to 0, then we would have 3x plus 5 times 0 plus 2 equal to z, which would be 3x equal to z. Oh, plus 2, sorry. Just threw that away like it didn't exist. The solution of this equation would be x equal to z minus 2 over 3, which would give us the ordered pair z minus 2 over 3 comma 0 as a solution to the equation for any value of z. Therefore, the range of the function is all real numbers over R. guess we will write that out and say range. So here's your domain, and here's your range. And I'm just paranoid that the thing is not working right now. Okay, so it is working. All right. Next one is going to be for part B. Oops. And we are given g of x, y is equal to the square root of 9 minus x squared minus y squared. So for the function g of x, y to have a real value, the quantity under the square root must be non-negative. So we know that 9, oh, sugar cane. We know that 9 minus x squared minus y squared has to be greater than or equal to 0. So from the inequality, if we change all the signs of everything, let's do that step first. Let's not change the values of things by making it wrong. No. Then we will move the 9 over. So we'll have x squared plus y squared greater than 9. Therefore, the domain of g of x, y is the following. So this leads us to the domain of g of x, y being xy has to be an element of r squared such that x squared plus y squared is in relation to 9. So this is the first part we need. Okay. The graph of this set of points can be described as a disk of radius 3 centered at the origin. The domain includes the boundary circle as the following graph. So, not sure why I didn't include that on the, oh, this is why, because it's a very long answer. All right, let me try to, you know what, we have slides, so I'm just gonna add a slide. That way we can have the drawing. So I will attempt to draw this for you guys. It's going to be a very, very rough sketch of this, and I think you guys are well aware of that. So we put our 3's in. -3, 3, 3, -3. And then actually, I think I can put in a, I think I can put in a circle. Okay. Oh, look at that. Oh, look at that. That's great. That's great, guys. Fantastic. I'm so glad that tool existed. Maybe I'll draw more stuff. Okay. So then that darker shaded area is x squared. Oh, it's going to keep doing it. Oh, I'll turn that off. Sure. I guess maybe wow, don't like that. I do not like that. Okay, how do I get this to go away? Okay, maybe it won't. Nope, just 1x squared. Nope, nope. Okay, so we're not going to mess with that anymore, and hopefully when I go to the next slide, it'll go away. If not, I might have to close it and reopen it. But you get the idea of that drawing. Okay, to determine the range for this function, we have to start at the point x sub 0, y sub 0 on the boundary of the domain, which is defined as x squared plus y squared equal to 9. So in other words, we would have, let's just go to the next slide. I really don't want this stuff right now. What if I come up here and hit this? Oh, perfect. Look at that. Now we're finding domain. Not domain, range. Okay, so we need to do x sub 0, y sub 0. So that means we would have x sub 0 squared plus y sub 0 squared equal to 9. So if we shove that into the g of x and make it this, we end up with 9 minus x sub 0 squared minus y sub 0 squared. Which, if we do 9 minus x sub 0 squared plus y sub 0 squared, we know that that is just 9 minus 9, which is 0. Okay. If x sub 0 squared plus y sub 0 squared equals to 0, in other words, if x sub 0 equals y sub 0 equals 0, then we would have the following. So let's write that out since it's our first time doing it. If x sub 0 squared plus y sub 0 squared equals 0, that's the same x sub 0 equals y sub 0 equals 0. Then that means that we would have g of x sub 0 or y sub 0 equal to 9 minus x sub 0 squared plus y sub 0 squared equals 9 minus, and you guys probably don't need all these steps, but I'm just giving them to you anyway. We may need another slide. This is the maximum value of the function. Given any value c between 0 and 3, we can find the entire set inside the domain. Okay. Of g. Okay, such that g of x, y is c. So in other words, we're going to add another slide. And we're going to have 9 minus x squared minus y squared equal to c. 9 minus x squared minus y squared equal to c squared. That gets rid of your square root. So then we'll change some signs. X squared plus y squared equal to 9 minus c squared. So since 9 minus c squared is greater than 0, this describes a circle of radius square root of 9 minus c squared centered at the origin. Any point on the circle satisfies the equation g of x y equal to c. Therefore, range is the interval between 0 and 3. Okay, you need all that work to figure that out. Okay, so we're going to go on to the next example. So part A. Create a graph of each of the following functions. So this is for part A. And that is g of x, y equal to our 9. 9 minus x squared minus y squared. Okay, so from the first example, we determined that the domain, so domain was x, y as an element r squared, such that x squared plus y squared had to be this. Okay, and the range was z in an as the element in all real numbers such that 0 greater than z greater than 3. When x squared plus y squared equals 9, we have g of x, y equal to 0. Therefore, any point on the circle of radius 3 centered at the origin in the xy plane maps to z equal to 0 in r cubed. So if x squared plus y squared equals 8, then g of xy equals 1. So any point on the circle of radius 2 square root of 2 centered at the origin in the xy plane maps to z equals 1 in r cubed. As x squared plus y squared gets closer to 0, the value of z approaches 3. When x squared plus y squared equals 0, then g of xy equals 3. This is the origin in the xy plane. If x squared plus y squared is equal to any value in between 0 and 9, then g of xy equals some other constant between 0 and 3. The surface described by this function is a hemisphere centered at the origin with radius 3. And I'm going to show you that. So, delete. So there is this. I can make it a little bit bigger now. So if you want any of what I just wrote out loud, or read out loud to you, sorry, I can give you some of that. So, first thing we have is x squared plus y squared equal to 9. Then that would give us g of xy equals 0. If z equals 0 in r cubed, then that gave us x squared plus y squared equals 8, would then give g of xy equal to 1. Equal to 1. Okay, and then as x squared plus y squared gets closer to 0, z approaches 3. So that would mean when x squared plus y squared equals 3, g of xy, sorry, not 3, 0. All right, then you pretty much know that if x squared plus y squared falls between 0 and 9, then g of xy will fall between 0 and 3. Okay, so then that gets us to the graph. Let's move on to part B. So this function contains the expression x squared plus y squared. Setting this expression equal to various values starting at 0, we obtain circles in increasing radiuses. The minimum value is 0. So min would be f of xy, which is x squared plus y squared equal to 0. That's telling us there that x equals y equals 0. When x is 0, the function becomes z equals y squared. When y is equal to 0, the function becomes z equals x squared. These are the cross sections of the graphs, and they are parabolas. So cross sections, and they are parabolas. Recall from the introduction to vectors in space that the name of the graph is a paraboloid. Just gotta spell that part right. Okay. And I have the graph for you. Okay. There it is. You guys can Okay. So that should be all good for you guys. Hopefully have enough time to draw it. All right, we're going to have another one where we draw, so I'll give you time for that too. Okay, so nuts and bolts. A profit function for a hardware manufacturer is given by f of x, y equals 16 minus the quantity x minus 3 squared minus the quantity y minus 2 squared, where x is the number of bolts sold per month measured in thousands, and y represents the number of bolts sold per month measured in thousands. Oh, nuts and bolts. Okay, sorry. Profit is measured in thousands of dollars. Sketch the function. Sketch the graph of the function. So the function is a polynomial function in two variables. Write that part down just for those who want to know. Polynomial function in two variables. All right. The domain of f consists of x, y coordinate pairs that yield a non-negative profit. Why can't we have a negative profit? Because that would be very bad for business. So we're going to assume their business is good. So we would have 16 minus x minus 3 squared minus y minus 2 squared, and it needs to be greater than or equal to 0. So do the same thing that we did in the other example. We're going to move the 16 and make everything positive. This is a disk of radius 4 centered at 3, 2. Okay. You guys should definitely have that screaming at you from working with circles. A further restriction is that both x and y must be non-negative. When x equals 3 and y equals 2, then f of xy would equal 16. Note that this is possible for either value to be a non-integer. For example, it is possible to sell 2.5 thousand nuts in 1 month. The domain, therefore, contains thousands of points, so we can consider all points within the disk. For any z greater than 16, less than 16, we would have the following. So if we're looking at z less than 16, we would have to solve for f of xy equals z. So we would have our, so let's start from this line because they just rewrite it. So, and then we would have x minus 3 squared plus y squared minus 2 squared. The squares right there, sorry. Equal to 16 minus z. All right, since we know this part, then we know 16 minus z greater than 0. So the previous equation describes a circle with radius. So this describes a circle with radius 6 square root of 16 minus z centered at 3, 2. Therefore, the range, starting to run out of colors, range of fxy is going to be z as an element in R such that z is less than or equal to 16. The graph of xy is also a paraboloid. and the paraboloid points downward. Okay. So let's get rid of this. All right. And you have all of that. I'm going to give you a few moments to, you can always pause the video, but okay. Let's keep it rolling. All right, so I just wanted to include this. You'll see it better in the PDF, or also if you look at the textbook, it's in there. I just thought it was really cool. I love whenever we bring in some of the stuff that's, obviously in the real world and such. All right, so we do have a definition down at the bottom though. It says given f, x, y, and a number c in the range of f, a level curve of a function of two variables for value c is defined to be the set of points satisfying the equation f of xy equals c. So our next example here, making a contour map. Given the function f of xy equals the following, find the level curve corresponding to c equals 0. Then create a contour map for this equation. What is the domain and range of f? So the first thing we want to do is we're going to want to set the function that we have given as f of xy equal to 0. So we're going to want basically to do f of xy equal to c, which is pretty much setting it equal to 0. So in this situation, okay. So we know if we can just get rid of the square root right off the bat. And the other thing we're going to do is so we'll just do all this stuff, so that's fine. So we'll do it like this. And then the next thing we're going to do is we're also going to multiply both sides by -1. So times -1 and times -1. So that's going to be able to let us rewrite it as y squared. Well, we'll put 4x squared up front plus y squared. Then we'll have minus x, 8x plus 4y minus 8 equal to 0. Okay. So now we want to rearrange the terms by putting the x terms together, y terms together, and then we want to move the -8 to the other side. So we're going to have 4x squared minus 8x plus y squared plus 4y equal to 8. So now we know that we will be factoring and know if we'd have to, we will have to complete the square. So 4x, we're going to pull that out and get x minus 2 plus y, and we'll get y plus 4 equal to 8. Nope, that's not how they want us to, they don't really want us to factor. They want us to fake factor. Because they want us to complete the square with it. So they only want us to pull out the 4. So I don't even know why they had us put parentheses around the second one. But 4, so that'd be x squared minus 2x. Not pulling anything out of the second one. And I understand why we're doing it, because they want us to do the completing the square. But I guess they don't really say to truly factor. They do say factor 4 from the first pair, which will make completing the square a little bit nicer, but still, really, you should be able to truly factor, but it's fine. All right, so bringing the 4 out, we would have inside x squared minus 2x, and then plus 1, and then y squared plus 4y plus 4 equal to 8 plus 4 times 1 plus 4. And we get that from this 4 out here. Righty. So next we will actually factor the left-hand side and simplify the right-hand side. So we would end up with 4x minus 1 squared plus y squared plus 2 squared. Sorry, the squares aren't really there. 8 plus 8 will give us a 16. So the next thing we want to do is we want to divide everything by the 16. So divide by 16, divide by 16, divide by 16. That will give us an x minus 1 quantity squared over 4 plus the y plus 2 quantity squared over 16 equal to 1. All right, we can repeat the same derivation, for values of c less than 4. So then this equation would become, so anytime c is less than 4, you would get 4x minus 1 squared over 16 minus c squared plus y plus 2 squared over 16 minus c squared, and that is also equal to 1. I'm just going to kind of try to move this over just a little bit. I didn't want to do that. So glad we learned about the undo button the other day, guys. There, we'll do it like that. Equals 1. Okay. So for any arbitrary value of c, this equation shows a contour map of f of xy using the values of c equal to 0, 1, 2, and 3. When c equals 4, the level curve is at the point. So we use, okay, so we would get, we use this when we have c equal to 0, 1, 2, and 3. When c is equal to 4, I'll just put it up here. C equals 4, we have a level curve at -1, 2. Okay, which makes sense if you look at the equation. All right, so this is what we end up getting. When we look at our level curve for this function. Okay. All right. We got to speed some of this up because I definitely am running out of battery power. So it looks like I was leaving myself some extra room to draw to keep going here, but you can see this continues that prior problem, which we don't have room for it on the other side, so that's fine. But I guess I didn't have to squeeze everything in. So here you can see that C of 0, C of 1, C of 2, C of 3, and then our C of 4 is that point, which was what, -1, 1, -2, 1, -2. So you have that all there now. All right. And just make sure you go through and do the homework problems on everything. You know, give you a better understanding. I guess I also thought I was gonna have to write on this slide. I'll just make this bigger. So definition, consider a function z f of x, y with domain being within r squared. A vertical trace of the function can be either the set of points that solves the equation f of ay equals z for a given constant x equal a, or the f of x b equals z for a given constant of y equals b. And you guys can see where that stuff comes from. All right, so we're gonna do another problem. I hope I can get through both of these without the tablet battery dying. Actually, let me see if I can plug it into a better electrical source. Oh, I can. There's one behind me. 1 second, guys. Okay. All right. Now that we have a better charging source. Oh, look, we're already getting percentages. Okay. So finding vertical traces. Find vertical traces for the function f of x, y equals sine x cosine y, corresponding to x equals negative pi over 4, 0, and pi over 4, and y equals negative pi over 4, 0, and pi over 4. So first, we're going to set x equal to negative pi over 4 in the equation. So if we, and we may need more than one slide for this. I don't know. It doesn't look like I gave myself extra, but we still have 3 more to play with. So first thing we're going to do is we're going to set x equal to negative pi over 4. So if we do that, we would have sine negative pi over 4 cosine y, which would give us negative square root of 2 cosine y over 2, which if you wanted the approximation there, that would be approximately negative 0.7071 cosine y. Oh my gosh, thank you. All right, so this describes a cosine graph in the plane x equals negative pi over 4. The other values of z appear in the following table. So if we make this table, I'm just going to actually include, so now you guys have seen how it works. I'm going to take this part off and I'm going to include it in the table. So we would have our C. They also include it in the table, but whatever, giving us more room. This is for the vertical trace. X equal to C. Negative pi over 4, 0, pi over 4. So we would have z equal to negative square root of 2 cosine y over 2, which we know approximated to that negative 0.7071 y. We would have 0, which would give us z equal to 0. And then we would have the positive square root of 2 cosine y over 2, which would be 0.7071 y. Okay, so that is for the x. So vertical traces parallel to the xy plane for the function f of xy sine x cosine y. In a similar fashion, we will also do the y. So we'll do d as negative pi over 4, 0, and pi over 4. And we're going to do the vertical trace for y equals d, not 9. I was going to do a 9 again, or whatever. D. Okay, so we would have z equal to the square root of 2 over 2 sine x, which would approximate to oh, I dropped off my cosines in the top. I knew something looked off. Cosine y, cosine y. All right, so that would approximate this to 0.7071 sine x. Y equals 0, right? Oh, sorry. Z equals sine x. Right. And then z equals the same as before, square root of 2 sine x over 2, which is approximately 0.7071 sine x. Okay, so the three traces in the xy plane are cosine functions. The three traces in the yz plane are sine functions. These curves appear in the intersections of the surface with the planes. X equals negative pi over 4, x equals 0, x equals pi over 4, and y equals negative pi over 4, y equals 0, and y equals pi over 4. So obviously our options, right? What we plugged in. And that becomes this. That's what your traces look like. Okay, so I'm going to give you a few seconds on that. Almost done with this one, and then we will move on. Okay, so part A. Domains for functions of three variables. Find the domain for each of the following functions. So we're given f of x, y, z as 3x minus 4y plus 2z over the square root of 9 minus x squared minus y squared minus z squared. Okay, so for the function to be defined and be of real value, two conditions must hold true. The first one is that the denominator cannot be 0, and the second is that the radicand cannot be negative. Combining these two conditions leads to the following inequality. So let me write those conditions for you. So the first is that the denominator cannot be 0. So that should be understandable to you. The radicand cannot be negative. Okay, so if we put those two things together, then we would get 9 minus x squared minus y squared minus z squared has to be greater than 0. Moving the variables to the other side and reversing the inequality gives the domain as. So the domain of f of x, y, z would be written as x, y, z as an element of R cubed such that x squared plus y squared plus z squared has to be less than 9. Okay. Which describes a ball of radius 3 centered at the origin. Note the surface of the ball is not included in this domain. So this is a ball of radius 3 centered at the origin excluding the surface of the ball. Okay, that's what the domain is. All right, part B is on the next slide. So we are looking at g of x, y, t given as the square root of 2t minus 4 over x squared minus y squared. So for this function to be defined, we have the two conditions, which, can I copy and paste those? I'm not sure. What are my options? Well, there they are again. We're just going to keep moving with them. Maybe. It just freeze. Okay. I just had to, I don't know, do a hard reset on the Jamboard. It just kind of froze when I tried to move those over. So again, we know that the radicand cannot be negative and that the denominator cannot be 0. So since the radicand cannot be negative, this implies that 2t minus 4 has to be greater than or equal to 0. So that would mean that t has to be greater than or equal to 2. Since the denominator cannot be 0, that would mean that x squared minus y squared cannot be 0, or that x squared cannot be y squared, which can be written as well as y cannot be plus or minus x, which are the equations of two lines passing through the origin. Therefore, the domain of G of g xt is equal to x, y, t. Oh yeah, all of them are in here. T. Such that y cannot be plus or minus x, and t has to be greater than 2 or equal to. And that is a t, not a z. A t. All right. So that is that one. We gotta roll. All right, here's our definition. Given a function f of x, y, z, and a number c in the range of f, a surface level of function of 3 variables is defined to be the set of points satisfying the equation f of x, y, z equal to c. All right, this is our last example for this section. And then I don't know if we're going to get in lesson 4.2 before the Penn State game, so we might have a second video. All right, so find the level surface of the function f of x, y, z equal to 4x squared plus 9y squared minus z squared, corresponding to c equal to 1. So the level surface is defined by the equation. Basically, all we have to do for this one is you say, okay, 4x squared plus 9y squared minus z squared equal to 1. And that's going to show the following set. It's kind of hard to see. I think you see it a little bit better in your textbook, and you see it in your on the PDF, obviously, but that's it. That's all you need are those fun kind of coney shapes. So I will see you in the next video where we will cover 4.2. Thank you for joining.